right, friends, we are back for week 5, 6. I don't know, the week of May 25th. So whatever that is. So I hope you all had a fantastic Memorial Day. And let's move on. This is our second to last major topic that we're going to cover this year. And this is exponential functions. So if you remember, we've looked at linear functions, we looked at quadratic functions. This is exponential functions. So tomorrow's lesson, we'll go through kind of comparing those 3, but today you have to be able to recognize and graph and write exponential functions. Okay, so the parent function, remember the parent function for linear functions was like y equals x, right? Or y equals mx plus b. For quadratic, it was y equals x squared. So for exponential functions, the parent function is y equals a times b to the x. So it's a little bit different because in linears, of course, you just have your x as a base with an exponent of 1. Quadratics, you have a x as your base with an exponent of 2. And in this one, your x is actually in your exponent. And a and b are numbers. So we do that as kind of a placeholder because you could just put a to the x, but oftentimes there is a coefficient there too, like a different coefficient. So we use a times b to the x usually. All right, so how to recognize? Well, there's 3 different ways. Exponential graphs grow very, very quickly. Or decay very quickly. So depending on kind of which way they're facing, so to speak. But there's also like a really leveled off part as well. So like an exponential function would start off like really like this and then just go and grow super fast. You can also tell it's an exponential function because x is in the exponent, not the base, right? So in linear functions and quadratic functions, it's in the base, and exponential functions in the exponent. The other way to tell is that if you have like a table of values, remember, because we always look at everything from equations and from graphs and from tables. So in a table, if you look at your y values, there's a common ratio. And well, what does that mean? Well, remember in linears, there's a common difference, right? So you're adding or subtracting the same thing every time. Common ratio in exponential functions means that you're multiplying your y values by the same thing every time. So instead of looking for something to add or subtract with your y values, you're looking to see if you're multiplying the same thing. All right, so for 1, 2, 3, we're just going to tell whether the following are exponential functions and explain why or why not. So if I take a look here, now what you want to do with a table is what you've always done with your linears and your quadratics. You first need to make sure your x's are going up by the same thing every time, still adding there. We're not multiplying anything with x's, and they are. -2, -1, 0, 1, 2, 3, 4, those are just adding 1 all the time. Now, I have 1/9 and 1/3. If you're good with fractions, you could do it from there, but what you might want to look at is the whole numbers because those are a little bit easier to tell. So if I look at 1, how do I get from 1 to 3? Can I multiply 1 by something to get to 3? Yes, times 3. Can I multiply 3 by something to get to 9? And the answer would be yes, that is also 3. And then if you're looking at to get from 9 to 27, can you multiply by the same thing every time? And again, yes, it's by 3, and then 27 to 81, etc. So now with these fractions, you can, at this point, assume that they were going up by 3, but also remember with linear functions, if we added 3 going to the right, we subtracted 3 going to the left, right? So like this way, we would have added, if we were going this way, we would have subtracted. Well, it's the same kind of thing. If you're going to the right, you multiply. If you're going to the left, you divide. So if I divide 1 by 3, do I get 1/3? Yes, I do. So I divided by 3 to get there. If I divide 1/3 by 3, do I get 1/9? Yes, I in fact do. So if I go to the left, I'm going to divide. If I go to the right, I'm going to multiply. Sorry about my dog. All right, so yes, this would be exponential, and the explanation is because there is a common ratio of 3 between my y values. All right, so now you can look at, these are coordinate points. Again, sorry for my dog. These are coordinate points. You can look at them as tables. Remember, we can just put them into a table if we want. Good practice here, reminding ourselves how to do that. So this is, remember, these are x's, these are y's. So this is -1, -5, then I have 0, 0, and I have 1, 5, and then I have 2, 10. All right, so let's take a look. Well, what do I multiply -5 by to get to 0? That would be 0. And then if I go 0 to 5, do I multiply by 0? I do not. So kind of like with linear functions where you found like if you're not adding the same thing every time, like in the second time, you can just stop. Same thing here. If I know that to get from -5 to 0, I have to multiply by 0. But if I multiply 0 by 0, I'm not going to get 5. I therefore know it's not exponential because there is not a common ratio between your y values. And if you're looking at this, you're probably realizing this is a linear function, right? -5 to 0, that's a +5. And then 0 to 5 is a +5. And 5 to 10 is a +5. So that's a linear function. So that's the other explanation you could have given is, instead of saying there's not a common ratio between y values, you could have just said, no, it's not exponential because it's linear. Okay. All right. Then we're going to take a look at this one. And again, make sure your x's go up by the same thing every time adding. They do. They go up by 1. And then if I take a look from 4 to 1, what do I multiply 4 by to get to 1? Well, that's 1/4. And then if I multiply 1 by 1/4, do I get 0? No. So this is not exponential. And again, your very simple explanation can just be that there is not a common ratio. This, if you look though, if you go 1, 4, 9, 16, what you might recognize is that's a quadratic, right? So that's just y equals x squared. And remember, just for fun, if I were to look and say, okay, 1 to 4, that's +3, 4 to 9, that's +5, 9 to 16, that's +7. Remember, there is no common difference. And then if I did it again and I found a +2, then I did have a common difference. So that's my second common difference. So that was what made it quadratic. It's been a while since we did that. And you certainly don't have to do that explanation, but that'll help for what we're doing tomorrow, like telling the difference between these. Okay. Now on the back of our notes, we are going to graph exponential functions. So like I said, our parent function is y equals a times b to the x. A is our starting point. And b is what you multiply by each time. You cannot multiply a and b together before raising it to the x power. That is a violation of order of operations, right? So remember, please excuse my dear Aunt Sally from like way, way, way back when. Exponents come before multiplication. So I'd have to raise b to the x and then multiply it by a. So pretend like b has its own little set of parentheses around it. Okay. All right. Now over here, a little thought bubble says a is always your y-intercept. Why do you think that is? Well, normally if we're in class, I'd make you guys think quite a bit about it. But what I'm going to do instead is I'm going to employ your knowledge of rules of exponents, right? So let's think about this. If I had y equals a times b to the 0 power, because remember, to be an x or to be a y-intercept, x has to equal 0, right? So if I plug 0 in for x, what was anything to the 0 power? And you guys hopefully are all shouting back, 1, Mrs. Shigley, it was 1. I remember that from chapter 7. Yay. So b to the 0 power will give you 1, right? So it'll be y equals a times 1, which is y equals a. So that's why that a value here is always your y-intercept. So if it's like y equals 2 times 3 to the x, your y-intercept is 2. Because if I were to plug in, oh my gosh, that's hilarious because I just did that. I did not even look at that. That's so funny. They're exactly the same. I don't know how I even came. That's hilarious. Okay. So if I did y equals 2 times 3 to the 0 power, 3 to the 0 would be 1, so be y equals 2 at x equals 0. Okay. All right. So let's fill in this little chart here. So we already know 0 because we just did it, right? So 2 times 3 to the 0. 3 to the 0 is 1, so that's 2. And then let's go, this will be 2 times 3 to the negative 1, 2 times 3 to the 1, 2 times 3 to the 2, 2 times 3 to the 3. If you weren't super great at like negative exponents and making them into fractions and stuff, then I might fill in like the positive exponents of this chart first and then kind of go backwards. So you can do each of these if you want, or remember you need the common ratio and then you can just do that. So I'm going to show you how to do it kind of the long way, so to speak, and then to show you using the concept of common ratios. So 2 times 3 to the first, 3 to the first is 3, times 2 is 6. 2 times 3 to the second, 3 to the second is 9, times 2 is 18. And then 3 to the third is 27, times 2 is 54. 3 to the negative 1 is 1/3. So 2 times 1/3 would be 2/3. Now, there is a much easier way to do this, right? So I know that this is my starting point. This a value is my starting point. So if I went y equals 2 times 3 to the x, that's my start. So x equals 0, that's my y value. Okay, so I can just fill that in right away. This b is what you multiply by each time. That is your common ratio. So exponential functions are super easy to read from equations because you have like all the information you need right there. So instead of doing 2 times 3 to the negative 1, 2 times 3 to the 0, 2 times 3 to the 1, 2 times 3 to the 2, I have one thing filled in. I have my 0, right? So I filled in 0, 2, and then I can go times 3, times 3, times 3. And then again, to get this, I just divide by 3 if I'm going backwards. So you can go backwards from 0, like, or up your chart by dividing your common ratio, and you can go down your chart or further on down your higher x values by multiplying. And then you graph. So negative 1 2/3 is a little bit tough to graph. So we're just going to put a point there. 0, 2, 1, 6. And I'm just literally like randomly putting points where I think they look like they might go. So like you can see, this is growing super duper slow. If you go to 2, though, you go all the way up to 18. And then if you have 3, go all the way up to 54. So that is where your growth is so fast, right? And it's because when you're multiplying by 3, like when you multiply 2 by 3, you just get 6. But then you're multiplying a larger, the 6 by 3 to get 18. Now you're multiplying 18 by 3 to get 54. And now you're multiplying 54 by 3, and you're going to get, 162 or what I think. So like the larger numbers you have, when you multiply them again, they're going to get larger and larger and larger. So you're going to and of course this goes on, and so does this. Now what's important to note is that this will actually never cross the line x equals 0. And there's a reason for that. And it's because and I'm so bummed that we're doing this online, because this is actually super fun activities to do in class with this. With I'll take a piece of string and cut it, and then cut it in half again, and then cut it in half again, and cut it in half again, and cut it in half again. You'll never get to 0, right? Because you can always take a smaller and smaller portion of it. Now, if you have an actual object, that's not necessarily true, because you'll get to a point where you can't cut half of the string anymore. But in theory, mathematically, you can always take a smaller and smaller and smaller amount. And at some point too, your calculator will be like, you know what, that's just 0, because it'll be like 0.000000002. And your calculator's like, whatever, that's 0. But it's not. It'll never get to 0, nor will it ever cross that line x equals 0. So on your calculators, it'll look like it just kind of becomes a straight line right here, but that's not 100% accurate. Okay. So y equals 3 times 0.5 to the x power. All right, well, let's just use our knowledge here. So remember, this is my starting point. So my x equals 0. So at x equals 0, y equals 3. Fill that in. And then this is my common ratio. Now, multiplying 0.5 is the same thing as dividing by 2, right? So if I multiply by 0.5, this will be 1.5. So, but if I go back up here, then I have to divide by 0.5, which really is multiplying by 2, right? So this will be 6. That'll be 12. That'll be 24. So when you see this common ratio of 0.5, it means you're just dividing it in half every time, right? So 24 to 12 to 6 to 3 to 1.5. And up here it'd be 48, etc. So this one's going to look a little bit different because instead of increasing really fast, it's going to decrease. So I have negative 324, and then negative 212, and then negative 1, 6, and then 0, 3, and then 1, 1.5. And again, you just assume that it keeps going and going and going close and close and close to 0, but never stops. Right? So this is actually called, and this will become important Friday, this is exponential decay. Decay just meaning decrease, right? And one that looks like this is exponential growth. So if it's growing, like if, and you, the reason you know is if this number is larger than 1. So if your B value is bigger than 1, it's exponential growth. If your B value is less than 1, it's exponential decay. Because what it means is like you're dividing, right? Because multiplying by a decimal is the same thing as dividing by that same fraction. Okay. So there are notes for today. And there's a couple of practices. I believe actually, I think I put both of these as practice. Well, all right. Let's just do this one. Sorry, I got a little confused there. All right, so this is kind of my own CUDA. I just put a table with it too. So I believe I'm just having you do the front end of this though. All right, so the first thing says evaluate each function of a given value. Well, f of x, remember that means y, right, is 1/3 times 6 to the x at x equals 2. So evaluate that just means plug in 2 for x, right? And then remember, you have to do your exponents first. So 6 squared is 36. And then 1/3 times 36, or 36 divided by 3, will give you 12. So that's what that means for evaluate. Excuse me. And then I'm going to go down here. So f of n, again, f of anything is y. So 10 times 2 to the n. So 10 times 2 to the negative 2. Well, 2 to the negative 2 is 1/4. So you have 10 times 1/4 is 10/4. And then, of course, reduce that to 5/2. Now, you can do all of these in your calculator, and especially those of you looking at number 4, like, no. You can certainly do those in your calculator. So this would be 1/5 times 1/3, where x equals 3, so to the third. So what I would do here is I would go, alpha y equals, okay, get a numerator denominator fraction there, so 1/5. And then times, and then get another one. And you can do this in parentheses. I probably would if I were you. So let's actually back out of that real quick. Go back. Oh, for the love, what am I doing? Okay, sorry. Okay, parentheses. Now I'm going to do alpha y equals. All right, 1/3. Oopsies. Boy, I'm a mess today. I'm so sorry. Okay. So 1/3. Why is it doing that? And then go out and close your parentheses. Yikes. Okay. Now we're going to raise that. I wonder if I had to do that already though. No, I don't. Sweet. I love these calculators. So I just hit the caret here because it's in parentheses. So no. So 1/5 times 1/3 to the third. Hit enter. You get 1 over 135. All right. If I want to do this one here, 10 times 2 to the n. So 10 times 2 to the 5th. 10 times 2 to the 5th. Boom. That's 320. And it'll, like, again, if you put it in like this, it'll just raise just that 2. So you should be fine. All right. And then these are graphing. So you have 5 times 2 to the x. Okay. So remember, that's your starting point. So where x equals 0, y equals 5. So you can put that right in. And then this is my common ratio, is 2. So everything higher than 0, so 1, 2, 3, I'm going to multiply by 2. So 5 times 2 is 10. 10 times 2, 20. 20 times 2 is 40. Here I'm going to divide by 2. So this is 2.5, 1.25, and then 1.625, I think. Hold on. I should be able to do this in my head. It's just like, it's so nice out, and it is 0.625. It's getting to my brain. Okay, so negative 3, 0.625, just, yeah. That should be a little closer to 1. Negative 2, 1.25. Negative 1, 2.5. 0, 5. 1, 10, 2, 20, and then 340 you can't fit on there, right? So remember, put your arrow here. And there you go. So if you want to do this one, you can too. What you should notice, since that's your b is less than 1, this will be a decay rather than a growth function. All right, and then your other sheet that you can do for homework is, these are just a bunch of different things, like a bunch of different concepts that we did. So if a golf ball is dropped from a height of 25 feet, the function f of x equals 25 times 2/3 of the x gives a height in feet of each bounce. What will the height of the golf ball be on the 6th bounce? Well, this is like a perfect example of a word problem having entirely too many words. So it wants you to take this and it wants you to evaluate it at x equals 6, right? So y equals 25 times 2/3 to the 6th. So that's all you have to do there. So I would do that one in your calculator. So 25 times alpha y equals 2/3 and then to the 6th. You got 1,600 over 729. And that doesn't like super help because it asks you to round to the nearest 1/10 of a foot. So I'm just going to divide those two. And I got 2.19 to 2.2. And what you could have done, if you didn't want it in fractions in the first place, you could have just, instead of like making it into the actual fraction, you could have just put it in parentheses and done 2 divided by 3 to the 6th. And it should just give you that. So if you put it in a fraction, it'll give you a fraction. If you put it not in an actual like fraction looking form, but just dividing, it'll give you that. So I should have done that in the first place. All right, 2, 3, 4, you're just explaining whether they're exponential functions. Your explanation should be common ratio or not. So common ratio between y values equals exponential function. If not, it's not. Graph each of them. You can do it through the tables if you want. Or again, if you have your calculator, but you would need to make sure that you are getting a table of values here from your calculator so you can do it. So 3 times 2.5 to the x, x equals n. And then graph. And it'll look a little bit different because notice like this is the window's different here. So it's -5 to 5. So let's change that. So x min -5, x max 5 goes by 1. Your y min looks like -8. Y max is 20. And that one goes by, well, actually it does go by 1s. You just only see the 2s. So if I graph that now, it looks a little more similar to it. And you can graph that from there. Remember, if you need a table of values, you hit second graph. And you can get your table of values there. So you know, like, okay, I'm going to do 0, 3. And then 1 is going to be at 7.5. If I want to go up further, like -1 was at 1.2. 2 is at 18.75. So as long as I have enough where I can see, you know, like how quickly it's growing. Okay. And then number 8 and 9, this is really what exponential functions are used for in real life, is like depreciation or interest, like in compound interest, simple interest, that kind of thing. You might have done that in economics with your personal finance unit. I'm not sure. We used to do it. I don't know. I can't remember if we did it last year or not. So we're looking at a family who bought 2 used cars, one domestic, so a U.S. car, and one foreign car. Domestic cars purchased for $11,600. So that's our starting point. Foreign cars purchased for $9,700. That's the starting point of that one. And the functions in the table represent the value of each car X years from now due to depreciation. So depreciation means like you assume, you know, the more miles you put on a car, the less it's worth, right? So what this is saying is that every year, so the domestic car you bought for $11,600, every year it's worth 88% of its original value. Okay. And then for the foreign car, you bought it for $9,700, and then every year it's worth 93% of its original value. So you just plug in again for these. So how much is each car worth 2 years from now? So you plug 2 in for each of those. And again, just do that in your calculator, right? I'm not going to make you do 11,600 times 0.88 to the second in your head. So your domestic car will be worth $8,983.04. And your foreign car, 9,700 times 0.93 raised to the second is $8,389.53. And how many years will the foreign car be worth more than the domestic car? Well, what I would do on that one is I would graph both of those. Because that's really the way that you know how to do that. Because you guys don't know how to solve exponential equations yet, because you need this concept of logarithms to do that. So 11,600 times 0.88 to the x for the domestic car, and the foreign car is 9,700. Oops, not 970, sorry, 9,700 times 0.93 to the x. So if I graph both of those, where I'm looking is that where this one is higher. Oh, I'm sorry. I'm not going to even remotely see those on a graph because of the window I have. Ooh, but what we could do is second graph and get a table. Maybe second graph and get a table. There we go. So what we're looking for, so my foreign car was my Y2, domestic was Y1. So looking for where Y2 is greater than Y1. So if you take a look here, almost, oh, right here at 4. So you see how the the domestic car is worth $6,956.50, and then the foreign car is worth $7,256.10. So at year 4, that's where the foreign car is worth more than the domestic car. So that's the way you can do that too. So you don't even really have to see the graph if you're looking on that. You can just look at the table of values and see where it jumps ahead. Okay. All right. Well, my friends, that is it for today. And let's see here. Where's my little stop button? I can never find this. It's like in a different place every time, and I really don't know why so much. All right. Peace out, guys. We'll see you tomorrow.